A uniform rod AB of length 4 meters and weight 80 newtons is smoothly hinged at end A to a horizontal floor. One end of a light inelastic string is attached to B and the other end of the string is attached to a horizontal ceiling. The string makes an angle of 60 degrees with the ceiling and the rod makes an angle of 30 degrees with the floor. The rod is in equilibrium, so we want to show all the forces acting on the rod. Well, let's take this end of the rod. Now, this end is attached to a string. Now, when an object is attached to a string, the string exerts a force on the object away from the object in a direction along the string. So this force will look like this. It's along the string and away from where the string is attached to the object. A string cannot exert a force in this direction. Okay, so we can forget about that. So that's the string force. Let's call it T. It's magnitude T. Now we have the force of gravity on the rod, or the weight of the rod, that acts at the center of gravity of the rod, which is the geometrical center because the rod is uniform. Okay, we will discuss center of gravity in later videos, but for simple situations like this, we just take it on trust that we can place the weight vector at the center of gravity, which is very easy to find for this case. It's just the midpoint of the rod, and its weight is 80 newtons, so we have the magnitude of this force. Now the rod is in contact with a hinge at point A. So what we can do is we can first consider the force on the hinge due to the rod. So you can see the rod is pushing on the hinge in this direction. So we could call this force here the force on the hinge H due to the rod R. And then we can apply Newton's third law. If there's a force on the hinge due to the rod, we must have an equal but opposite force on the rod due to the hinge. Now, it would be much easier to break this force into its horizontal and vertical components. So in general, that's what we want to do. It's often easier to get moments when we just consider the horizontal and vertical components. So I will remove this here and replace it with its components. So its horizontal component looks something like this, and here's its vertical component. Okay, so I just resolved this vector into its horizontal and vertical components. I'll call the horizontal component x, its magnitude is x, and let the magnitude of the vertical component be y. Okay, we are going to write down the two equations that arise from resolving the forces horizontally and vertically. So the rod is in equilibrium, so that means the resultant force on it is 0. If that's the case, the sum of the upwards forces acting on this rod must equal the sum of the downward forces acting on it. So what are the upward forces? Well, we have y. Well, the magnitude of this vector is y. It's pointing up. We want the upward component of vector t. So that's this component here. Well, what's this angle in here? It's the same as this angle here. These are a pair of corresponding angles. This is 60 degrees. Okay, so this line here is horizontal parallel to this line. So we have this right angle triangle here. It's a bit small, but we want the side that's opposite 60 degrees in this right angle triangle. So we have to multiply the magnitude of t by the sine of 60 degrees. So this is t sine 60. Okay, it's pointing up the way. So we have y plus t sine 60 for the sum of the upward forces. You can see that we can resolve vector t into this upward component, t sine 60, and actually a horizontal component as well, pointing to the left. So if we add these two vectors by the triangle law, we will have vector t. Okay, we'll get back to the horizontal component. So those are the upward pointing vectors. Well, the sum of the magnitudes of the upward pointing vectors. And that must equal the downward vector, which has magnitude 80 newtons. Okay, x has no vertical component. So if we add the magnitude of this vector onto the magnitude of this blue vector, we must get 80 for equilibrium. Okay, now let's look at the horizontal forces acting on this rod. Well, we've got two of them. We've got the horizontal component of vector t, which points to the left, and we have vector x, which points to the right. And they're the only two horizontal forces acting on the rod. They must be equal in magnitude. So we can see straight away that the vector pointing to the right has magnitude x, the vector pointing to the left, well, that's the side adjacent to 60 degrees in this right angle triangle. So we multiply the hypotenuse, which is t in magnitude, by the cos of 60. You can see straight away that this diagram is not very accurate, of course. This vector here, this green vector t cos 60, must be equal in magnitude to x. So maybe I'll just tidy this up to make it a little bit more realistic. Now, so all we did here was apply the equilibrium condition that the resultant force is 0. Okay, so that's one of the two equilibrium conditions. And we get equations that cannot be solved. There are too many unknowns. There are actually 3 unknowns, okay? X, t, and y, but only 2 equations. If we just had 2 unknowns, we could solve these equations. So we cannot find x or y or t yet. We need to apply the second equilibrium condition, which involves moments, okay? The turning effect of these forces, because this rod is not rotating. So, so the sum of the moments of this rod about any point is 0, or another way of saying that, as we saw in a previous video, is that the magnitude of the sum of the clockwise moments is equal to the magnitude of the sum of the anti-clockwise moments about any point. So this is the relation that we saw in the previous video. So now we can pick any point we want actually, but as I explained before, you should pick a point that's convenient, that minimizes the number of moment calculations that we can do. Okay, it'll work for any point, but the most convenient point is point A, because the moment of the forces y and x about this point are 0. That's because A is on the line of action of both of these forces. So the perpendicular distance of A to both of these forces is 0. Okay, so let's get the forces that give a clockwise moment about point A. Well, the 80 Newton force is the only one actually. This acts to turn the rod clockwise about the point A. So what do we do? Well, we multiply the magnitude of the force, which is 80, by the perpendicular distance of A to the line of action of the force. Okay, so we want this distance here. Well, that's easy to find because the rod is 4 meters long. And since this point here, the center of gravity is at the midpoint of the rod, we have a right angle triangle here which is half the size of this bigger right angle triangle. So we just get half the sides of it. So in this right angle triangle, we want the side adjacent to 30 degrees, so we multiply the hypotenuse, which is 2, by the cos of 30. So this distance here is 2 cos 30 degrees. So we multiply 80 by 2 cos 30 degrees. And the 80 Newton force is the only force that has a clockwise moment about the point A. Now, the other force that we have to consider is T. What about the moment of T about point A? Well, actually, that's an easy one to do. Or is it? Well, we have to multiply the magnitude of T by the perpendicular distance of T to the point A. Is this a right angle? If this is a right angle, we have a straightforward calculation, because the perpendicular distance of A to the line of action of T will just be the length of the rod, which is 4 meters. So we just multiply 4 by T. Let's prove that this is a right angle. Okay, so how do we do that? Well, let's draw in this horizontal line here, passing through the point B. So this dotted line is parallel to the horizontal, so that means that this angle is the same as this angle here. It's 30 degrees. Okay, these are a pair of Z angles. But we have another pair of Z angles up here. Okay, so this dotted line is parallel to this line up here, so this angle must be 60 degrees. And we see that 60 plus 30 gives us 90. So that's very handy. So the perpendicular distance of point A to the line of action of T is just the length of this rod, which is 4 meters. So we multiply the magnitude of T, which is just T, we don't know it, by 4. And that's the only force that has an anti-clockwise moment about the point A. So that's the direction of rotation when we apply force T. That's the direction of rotation about to point A. So that's the only. If we had other ones, we would have to add them on here. We have to get the sum of them. But we only have the one of them, so we don't have to do any summing there on the right hand side. So straight away we can see we can solve this equation to find out what t is. T is the only thing that's missing. Okay, so we have 80 times 2 divided by 4. Well, that's half of 80, which is 40. Now the cos of 30 in surd form is root 3 over 2. So we get 40 times root 3 over 2. So in surd form t is 20 root 3. So we have answered parts 3 and 4. Now in part 5 we want the magnitude of the reaction at the hinge A. So that's, we basically want to, we want to start by getting the magnitudes of these two forces, x and y. Well, that's where we go back to these two equations now. We found one of the unknowns. We found what t is. So we can plug it into these two equations. And from that we can find out what x and y are. Okay, so into this first equation I've plugged in t equals 20 root 3. Okay, so we bring the 20 root 3 sine 60 over, so we get 80 minus 20 root 3 sine 60. In surd form, sine 60 is root 3 over 2. So we've 2 into 20 here goes 10 times. So we've 80 minus 10 times 3. It's 80 minus 30, which is 50. So there's y. And now let's get x. So x is t. T is 20 root 3 multiplied by the cos of 60. The cos of 60 is a half. So x is 10 root 3 newtons. So now we can answer part 5. We found the components of the force on the rod at A. Okay, it's along this direction as we saw earlier. Well, I mean, it's supposed to be the sum of these two forces. I'll just try and make it some bit realistic looking. So we add these two forces by the parallelogram law and we get this force here. So this is what we're after. So we will call this force, well, we'll call its magnitude R. So I'll draw it out down here. Right, so here's the picture. So this is 50 newtons, that's y, and x is 10 root 3 newtons. So what's the magnitude of this vector? Well, simple application of Pythagoras' theorem. Okay, because these two forces are at right angles to each other, so this side here is also 50. So two short sides are 10 root 3 and 50. So get the square root of the sum of the squares of the two short sides. Okay, so in surd form, the answer is 20 root 7 newtons. So that's the magnitude of R. A uniform beam AB is held in a horizontal position by two vertical inelastic strings attached at points C and D respectively. The weight of the beam is 45 newtons. So since it's uniform, we put the weight vector acting at the center of gravity, and as I said before, we'll cover that in later videos. Center of gravity is just a geometrical center of this line AB, since the beam is uniform. The mass is uniformly distributed through it. So this vector has magnitude 45 newtons. A particle of weight 10 newtons is attached at A, and a particle of weight 15 newtons is attached at B. The distance of A to C is half a meter, the same as the distance of B to D. Now, the beam is 2 meters, so the distance of C to this point here must be a half. Okay, because the center of gravity is a distance of 1 meter from the ends. This must be a half as well, distance from here to D. Now, this beam is in equilibrium. The resultant force on it is 0, and the sum of the moments of the forces about any point on it is 0. Or we could say that the sum of the clockwise moments is equal to the sum of the anti-clockwise moments about any point. Okay, so these are obviously not the only three forces acting on it. If they were, the beam would accelerate downwards. We have a force on the beam at point C due to this string. Okay, so the force on an object due to a string is away from the object and along the string. Let's call the magnitude of this force T1. Similarly, we have a force here, not necessarily the same as this force, and actually you can see that we don't have any symmetry here. We have a slightly greater force on the right hand side, so we would expect that this force has greater magnitude than T1. Let's call it T2. So we want the tension in each of the strings, so let's use the first of the two conditions for equilibrium. The resultant force must be 0. So it's very easy here to add up these forces, they're all in the vertical direction, so the forces up are given by T1 plus T2 must equal the sum of the forces down, 10 plus 45 plus 15. So we get 70 for that. Okay, so the resultant force is 0, so that breaks down to the sum of the magnitudes of the upward forces equals the sum of the magnitudes of the downward forces. Of course, we have two unknowns here, so we can't solve. So we use the second condition for equilibrium. So we consider taking moments about some point. Now we can take the moments about any point, but let's see. Let's take moments about point A. You could use B as well. It doesn't really matter. Both are equally as involved in the in doing the calculation. You could also take moments about C. I might try it a different way as an aside later on. Let's take moments about point A. So we apply our formula. So we need to consider clockwise moments of forces about point A. So what forces give clockwise moments about point A? Well, it's these two forces here. The 45 Newton force acts to turn this beam clockwise about point A, and so does this force here. The other two forces, T1 and T2, turn the beam anti-clockwise about the point A. Okay, so let's get the moment of T1 about the point A. So we take the magnitude of T1, which is T1, and multiply by the perpendicular distance of the line of action of T1 to A. Well, that's just a half. Very straightforward here. Okay, that's sorry, I have this the wrong way around. That's an anti-clockwise moment. That should be on the other side. Okay, I'll do the anti-clockwise one over here. T1 times a half. And T2 is anti-clockwise as well. So we multiply its magnitude T2 by the perpendicular distance of A to the line of action of T2. Well, that's a half plus a half plus a half, which is 3 halves. You see, these strings are perpendicular to the beam because the beam is at rest in a horizontal position. Okay, so we multiply T2 by 3 halves. So that's the magnitude of the sum of the anti-clockwise moments. Now let's take the clockwise moments. So it's 45 Newton force is a clockwise moment, so we multiply its magnitude, 45 by a half plus a half, which is 1, and we have the 15 Newton force as well, multiplied by half plus a half plus a half plus a half, that's 2. Okay, so there are two clockwise moments that we have to sum and take their magnitude to make it positive, because clockwise moments are actually negative. So that's it. Magnitude of sum of clockwise equals magnitude of sum of anti-clockwise. So we have a second equation in two unknowns, T1 and T2. So on the left hand side we get 75. If we multiply all of this by 2, we get 150 equals T1 plus 3T2. So you see we have two equations in two unknowns. So we just solve between these two equations to find T1 and T2. So a quick way to do that is to write this equation down underneath the second equation and simply subtract 150 minus 70, and over here when we subtract, these go out. That's what we want, and here we get 2T2, so T2 is 40 newtons. Since T1 and T2 add to 70, T1 must be 30 newtons. So here's the final picture. Now, as an aside, I will repeat this problem by taking moments about the point C. That way we can get T2 directly. So, what are the clockwise moments about C? Well, this force has a clockwise turning effect about C, and so does this force here. Okay, they both act to turn the beam clockwise about the point C. T2 turns it anti-clockwise actually, and so does this force here. Okay, so let's get the moments of these two forces, and we have to sum them. So we have to multiply 45 by a half, and for this one here we have to multiply 15 by 3 halves. Now let's take the anti-clockwise moments. Well, the 10 Newton force is an anti-clockwise moment, turning effect of the beam about the point C. So we multiply 10 by a half, Now what about T1? Well, T1 has no turning effect. It's T1 times 0 because its line of action passes through C. The perpendicular distance of C to the line of action of T1 is 0. What about T2? We multiply T2 by a half plus a half, which is 1. You see, now we have an equation and just one unknown T2. We can solve for T2 directly. So if you solve this here, you get 45 minus 5, which is 40 newtons. And then you can just plug up here to get T1 equals 30 newtons as before.